Thank you, Kat. Good morning, good afternoon, or good evening, depending on where you are in the world. Thank you very much for joining us today for this very interesting webinar that will be provided by Gus. It obviously shows that this is a topic of interest because we've had 129 registrations to this webinar. I'll give a very brief introduction to Gus, who I've known for nearly 3 decades now. Gus is an independent Metocean consultant who has a wealth of experience in both underwater, but also in the atmosphere. And the atmosphere really started, I guess, when we worked together on a project called the West Africa Gus project in West Africa to try to better characterize winds for offshore design. Since that time, he's used that knowledge and really moved into the offshore sector, offshore renewable sector, contributing to the IMarEST Metocean Procedure Guide for Offshore Renewables and also the American Wind Energy Association Metocean Recommended Practice. He's also been running a joint industry project on extreme and normal offshore winds as part of his own company, Oceanalysis. And with that, I'll hand over to you, Gus. Thank you.
Thank you very much, Mark. And thank you also to everyone who's joining this discussion today. This webinar, I think, is a small part of a much bigger discussion on this topic, a discussion that's been going on since wind energy started moving into the offshore regime several decades ago. There's several different angles at which you could approach this topic, and as this is an IMarEST webinar, the angle that we're looking at here is in terms of knowledge exchange. Excuse me, knowledge exchange between two technical disciplines of the wind resource technical discipline and the Metocean technical discipline. So I'm gonna talk through my perspective on these disciplines. Okay, so there's 3 broad areas I'm going to cover. I'm going to look at the sort of evolution over time to some extent of these 2 separate technical disciplines, and then make it very clear that my perspective is from the Metocean side. That's where I've worked, but I'm trying to actively engage and communicate very widely with the wind resource community as well. I'm going to then dig deeper into some technical issues, first looking at the way measured data and numerical models are used to quantify winds. The whole subject here is the quantification of offshore winds within the wind energy community, within the wind energy industry, but for different types of application. The application of quantifying the wind as a resource, and the separate application of quantifying the wind to plan your operations and engineering design. And then continuing the theme of technical content, I will look at vertical profile relationships and something about methods used to derive extreme winds. Okay, so Mark's already mentioned this, talking about my own perspective. Is a Metocean perspective. I've been involved in this discussion for the wind energy industry, so going back nearly a decade, when I became involved in the Offshore Renewables Special Interest Group. And one of the first things that we did in collaboration with the Operational Oceanography Special Interest Group, which I was a co-chair of for some time a little bit before that, was to produce now 2 iterations of this Metocean Procedures Guide for Offshore Renewables. The link to that, the most recent guide, is there. These slides also, I'm happy, and I've approval from material I've used to distribute in a PDF form afterwards. So this guide, you can Google Metocean Procedures Guide and you'll find this. So I'd strongly recommend people look at this if they're not already familiar with it. At the time we produced this, it was nearly 10 years ago, the first edition, and it originated from a piece of work that one of our members of the Operational Oceanography Special Interest Group, Ian Leggett of Ocean Expert, had produced from his extensive Metocean experience in oil and gas primarily, but also a little in offshore wind for one particular offshore wind developer. And it was within the IMarEST, it was very much a knowledge transfer initiative of transferring knowledge from the extensive Metocean techniques that have been developed primarily to support oil and gas, and how these can be used to quickly and effectively reduce the cost of, at that time, the very rapidly growing offshore wind energy industry. So that document's in its second iteration, and it needs updating again. It's still quite biased towards European waters. So we have it on our agenda to update this living document. And in connection with this, also, as Mark mentioned, an initiative I've been involved in, again, on a voluntary basis entirely, with Mark as well. Mark contributed towards this. I heard about a Metocean recommended practice being developed by what was then the American Wind Energy Association, now rebranded as American Clean Power. And I offered to help develop that. And a group of us also helped develop that recommended practice, which should be published later this year, I think. I'm not sure if we have any. We did invite several of the people from the relevant Metocean data analysis working group to join this webinar. If they haven't been able to get up early enough to join, then a little hello in the Slido would be nice to know if you're there. It'd be nice to get some input on this from across the Atlantic. We're holding this meeting at a time of day when we're hoping to make it possible for a lot of the corresponding members from the IMarEST special interest group are in the Asian region, but hopefully it's also possible for some people to join from across the Atlantic. So this slide is, I will begin to explore the different perspectives between resource assessment and Metocean. As I said earlier, resource assessment is really about quantifying the wind to determine how much energy can be generated from it, whereas the Metocean perspective is in terms of operations and design. So this graph here shows a sort of typical wind energy power curve, which is fundamental to wind energy engineering. Basically, at low wind speeds, you don't get any energy out of a wind turbine. You need the wind to ramp up to a particular wind speed. And then once it gets to an operating wind speed, then it kind of plateaus and it doesn't generate any more energy. And then at certain higher wind speed, it basically shuts down. And at that point, you have too much wind. So the resource community, wind resource community, are obviously primarily involved in making sure they understand this low end of the wind speed spectrum. And often the Metocean community, particularly for engineering design, are looking at the high end and the extreme wind speeds, but also the stronger wind speeds that could prevent operational difficulties. And if you're making an estimate of wind speed from either of these technical disciplines, these different applications, in the presence of uncertainty, which always exists, particularly at the early stage of any project, you generally make a conservative estimate, which means erring on the side that has the least adverse consequences. And those go in very opposite directions. A conservative estimate of wind speed for a resource assessment will be a low estimate of wind speed, and the converse is true for operations and design. And this provides an important point to just understand that there is a natural difference in the perspectives here in terms of the application. That doesn't mean that they should have different estimates. A lot of effort will be made to make sure that the estimates should be consistent and that perhaps the conservatism should be applied later in the analytical workflow. But there have been cases that perhaps many people on this call will be aware of, where these two perspectives could lead to different estimates being made due to different interpretations of conservatism. And as I'll explore soon, the different estimates can also be made because completely different data sources and analysis methods can be used as well, which is something that if we can aim to reduce that, then we can make the whole process more efficient and reduce the cost of offshore wind even further. Another point, because the wind is the resource in this case, there can be a lot more sensitivity about the wind data. And the Metocean community, as it developed in oil and gas, had developed over the years lots of data sharing initiatives, and there's some of those exist also in the wind resource, wind energy community, but there's greater sensitivities there, and it can become a little bit more complex, particularly at early stages of the project. So looking at these two technical disciplines, as I've outlined, wind energy resource assessment, by which I also kind of mean the wind energy design process as well, it takes a lot of its methodologies from the resource domain as well, I think, have evolved separately over time, going back perhaps the lifetime of more than lifetime of my career, the lifetime of my whole life. So both of these disciplines have been emergent since sort of 1970s, into when the wind energy, onshore wind energy, was really growing and starting and developing. And most of that, as I said, wind energy started onshore. And one of the key things that impacts the wind regime is the terrain. And there's very, very large variations in the wind regime through the horizontal and the vertical due to the terrain onshore. Compared to the offshore regime, the ocean certainly changes in time to a very large degree, but in space it is generally much more uniform than the terrain onshore. And that has important implications for the way you select data sets and analyze the data. Also, historically, the wind resource and wind energy onshore tradition would be able to find some measured data, long-term measured data at some sort of reasonably representative location. You would have to make corrections to that, and established techniques were developed to correct a long-term reference data source to your particular location, taking into account the large variations due to the terrain primarily, but also other factors. But whereas in the offshore world, where Metocean tradition evolved, there's generally much less long-term measured data sets in the offshore regime. And of course, the offshore winds are generally stronger and actually more preferable for generating wind energy. So to get you can't use onshore data and assume that it's representative of the offshore location, the offshore development region. There's generally much less measured data offshore, which means there's been, from a very early stage, a higher reliance upon numerical models for quantifying both extreme and normal winds. So, of course, in terms of applications, as I've said already, in the wind resource, wind energy community, the wind is the resource. So there's a great deal of effort put in at an early stage to quantify, particularly the mean wind, for the project feasibility. Whereas in the Metocean tradition, winds certainly do create an important design case for some structures, and particularly in some regions. But quite often, winds have been more important to quantify because they're the key driver for generating waves. So that's another difference in the way that these different technical disciplines have evolved. Another thing that's important to consider as well, for an offshore wind development, there will be a large array of turbines generally, and so wake effects are very important to understand for the energy yield, not just within one particular wind farm, but also the influences of other nearby wind farms. And in parts of the North Sea now, there's an extensive amount of development, and it's in some places it's difficult to find a piece of sea that's not impacted by the wake effects of one wind farm or another. Whereas in the Metocean tradition, you're primarily interested in quantifying the clean wind, the undisturbed wind in the absence of structural effects. Whereas in the wind resource community, wind energy community, there's an enormous amount of effort goes into understanding and quantifying these wake effects. As I've already said, really, it's should follow the focus in the wind resource community is on quantifying the mean wind, the normal winds. So what's likely to occur on average over, 1, 10, 20 year period. We're looking also at, seasonal and diurnal variability, of course. Whereas a lot of the focus and analysis effort in the Metocean community has been looking at extreme events. And a lot more effort is put into deriving extremes. And then the last two boxes here, these are, I'll talk about these in a moment later. Two particular methods have evolved, which I will argue shortly are essentially the same: the measure, correlate, predict, and wind model validation. I'll talk about those again in a minute. The point of this slide is to try and illustrate that there is some convergence here between these technical disciplines. So still in this introductory stage, looking quickly at the international standards that are used to determine how each of these methods should progress to quantify the wind. So the IEC, actually, before I go into that, I'll just say one of the things that I'm also involved in on a voluntary basis again is I've become involved in the relevant TC88 IEC committee. Because I'm based in the UK, that's via the British Standards Institute. So I'm now becoming involved in the relative committees and shadow groups that will feed into these IEC standards. So that's something underlying my interest here. So it's worth mentioning. I think there may be some people joining this webinar who are also involved in that may wish to comment or ask questions. So the IEC guidelines are the primary source for engineering design of wind turbines. And so there's this 61400 series, and -1 stipulates the generic design requirements for a turbine, which is by default onshore. And then over recent years, there is this -3, recently expanded to be -3-1 to look at fixed offshore wind turbines. And then there is another document in evolution that's not yet a full international standard. It's a technical specification at the moment, the -3-2 series, looking at floating offshore wind turbines. So these documents do stipulate quite a lot of detail of the procedures that should be considered and undertaken in the design of these structures, these turbines, and the underlying support structures. It's also worth mentioning here, there's a whole series of a large number of different working groups and document series within the IEC standards. But another one that's relevant to this is the -15 documents, which again are in development, but they're looking more at site suitability input conditions, and that has an input on the wind resource. So within the engineering design and wind resource communities, there's already some differences in the approaches to the way things may be done that to some extent may be reflected in different parts of these IEC documents. Then coming from the long established Metocean tradition, which, as I said, was primarily evolved to support oil and gas, one of the primary documents is the ISO 19901 document that gives, for the Metocean practitioner over many years, this is kind of our primary source document of, we should be complying with these procedures and following the methods that are outlined within. And a lot of consistency, a lot of effort has already been made, I have to say, to ensure the relevant wind turbine, offshore wind turbine, both fixed and floating standards within IEC are consistent and cross-reference relevant parts of this. But there may be some areas for further convergence, and I'll explore a few of those later. Also worth mentioning, it's not a fully international standard, but it's a little bit more up to date. The API produced the RP2 MET document, which is the most recent update in 2019, the same year as the batch of the most recent IEC standards. It's more recent than the ISO document. It's again entitled Derivation of Metocean Design and Operating Conditions. It has a lot of information specific to the US region, so that's obviously important because a lot of work's been done there to understand the Metocean regime. in those regions. It has some more up-to-date information in that document than ISO in terms of wind profiles and turbulence intensity. And other than that, the core document follows very similarly the ISO document. They're designed to be consistent. So that's important background. This is a slide that I think there should be some people from DHI on this, joining this webinar, that have worked on a large number now of public domain metocean studies, and the Netherlands Enterprise Agency, RVO, have really taken what I would consider to be a sort of almost a global best practice role in terms of how they provide a whole suite of site information, including a Metocean, comprehensive Metocean criteria, including measurement programs and modeling analysis and design criteria, in advance of a project being put to tender. This is a very successful model that it would be great if the UK and other places could adopt something similarly. So there's an enormous amount of information in the public domain. The Metocean studies have been undertaken by DHI primarily, and there's a link there to one of their most recent products, one of their most recent public domain Metocean criteria reports for the Hollandse Kust West development that's now being taken forward. And these pictures are taken from an appendix from their report, which is specifically dedicated to the topic of wind resource assessment alignment. So basically, the Metocean and the wind resource analyses are usually undertaken separately to some extent by different organizations. That's very common, using potentially quite different methods and data sources. But then, and this, as some of the relevant people involved in this may explain, you know, this process of communication between these organizations is perhaps improving over time, and a great deal of effort is then made to make sure that they're aligned appropriately. And all of the numbers in this table are related to an estimate of the long-term mean wind at a number of key points around the wind farm development location, and looking at the bias from the different sources. I'm not going to talk in detail about that. I just wanted to make it clear that a lot of effort is already done in this area, and this is a very recent public domain example. And so it's, you know, it's really great that the Netherlands Enterprise Agency and DHI and the other Tractebel also are involved in the wind resource here, are putting these documents out in the public domain. They're very useful for other professionals to have a look at what's been done. I should also say that these particular reports are also certified by DNV GL, as they were at the time, and which also, of course, gives it much, you know, robust credibility. So I said earlier I'd mentioned the measure, correlate, predict, and model validation a little bit, because this is an example of different terminology that's used in the wind resource community and the Metocean community, which I'm arguing here are essentially the same thing. So this plot here shows, from the context of measure, correlate, predict, we're looking at some sort of correlation between the long-term measured wind speed at a reference site. So this could be maybe, you know, decades of wind data from a nearby airport, and then some short-term measured data set from your target site. So you look at some correlation between your short-term measured data representative of your site and some long-term reference time series. This just shows probably the most simple possible way of deriving a correlation. When there is a simple correlation, you can do a simple linear regression or scatter plot or quantile plot and derive a simple linear relationship. Obviously, it's often much more complicated, and a whole range of different methods could be used and are used to derive these relationships. But the key point is you're trying to derive a robust relationship to put your short-term measured data into the long-term context, or to make sure your long-term estimate of mean wind for the wind resource application is representative of your target site. So that illustrates the concept from the perspective of wind resource, measure, correlate, predict. But in fact, if I just strip away the axes labels, this is actually just a plot of model wind speed from the ERA5 global wind model at 100-meter elevation, plotted against, in this case, 3-hour mean measured wind speed, effectively the same location. So in fact, this is, in the Metocean community, what we call model validation and calibration. I should be specific that this is wind model validation and calibration, because in the IEC documents, model validation often means models of a turbine. So again, we have to be careful of the terminology. So I perhaps should have been a little bit more careful, but in the Metocean discipline, we would just call this model validation and calibration, or model correction, or other terms can be used. But the key point here is these two pieces of terminology are basically describing a very, very similar analysis technique, and that's something that I think is one of the things I'm trying to raise discussion of today, is to trying to bring these communities together and to understand that they may be talking about essentially the same thing often, but using different words and having different perspectives. So moving into the modeled data topic in more detail, there's a lot of discussion around, particularly in the wind energy community, about global, well, particularly mesoscale and microscale models. There's some documents that I've seen from the wind energy that almost indicate that to get an accurate estimate of the winds at a particular site, you have to use a mesoscale model at least, or preferably a much more finer scale microscale model to accurately represent the conditions. And what I'm trying to make the point here is that in the offshore regime, you can actually often get almost as good results from a global model. There are there are a handful of very widely used global models, reanalysis models covering several decades at a resolution of, several grid points per degree, so through tens of kilometers resolution. ERA5 is one of the ones that's used very commonly. Others include CFSR and IMarEST. And these are off-the-shelf global wind models that are your first point of call for looking at wind climate in a particular region if you have no other data. These plots here on the left show a comparison of long-term mean wind from the study, this new European Wind Atlas publication. The full details of it are there below the plot, between this ERA5 global wind model and a very extensive downscaling that was undertaken for this new European Wind Atlas study of this region using the WRF, almost the industry standard downscaling to mesoscale. And the key point there is looking at the difference. You can see over the mountainous regions, there is a notable difference in the mean wind speed. But in fact, in the offshore region, or most of the offshore region, particularly if you go a little distance from the coast, which you can hardly make out the coastal region at this scale, there's very, very little difference. So this is part of the evidence that you can often get a good estimate of your wind conditions in the offshore region using a global model. Certainly for the mean wind, it's easier to characterize the mean wind than the extreme wind. And then on the right, there's a further downscaling to microscale using WASP. And again, that's comparing the mesoscale WRF with the microscale WASP. And again, the difference then is again really confined to the areas with very, large variations in the terrain, where you need to resolve those variations in the local ground terrain bathymetry, topography, sorry, to resolve the wind speed, the wind variations. Okay, now I've got several slides to explore. I've actually been going for half an hour, haven't I now, Mark? Pretty much. So, I if I'm not careful, I'll use up all the time. I put extra slides in thinking that that I might need to bulk out my slides, but I'm obviously talking quite a lot, so I'll try and speed up a little bit to make sure there's time for discussion. So there's a few slides now talking about various methods that are used in wind energy, wind resource community and the Metocean community to simulate the short-term variability, which isn't captured by a model, particularly if you have one of these global models I've described. The spatial and temporal resolution just will not resolve the short scale processes and the short in space and time that you need to capture peak events. So I'm initially going to talk about the characterization of peak wind speed events for the estimation of extremes, rather than looking at normals. And this is again an extract from one of those public domain Netherlands Enterprise Agency studies. Again, this one's for Hollandse Kust Noord. Again, the Metocean study was produced by DHI and certified by DHL. This is for a different location, but it's one that I've looked at more closely, so I included this in this slide here. And this shows the wind spectra, so the energy density within the wind, calculated as a function of frequency along the horizontal axis, and the measured data, the raw observed data at 10-minute mean follow this line here, and if you average those over 1 hour in blue here, you get a loss of energy at the high frequency, and then in green there's a line here that also shows if you average the measured data over periods of 2 hours, if you take 2 hour means, you get a loss of energy. And so this shows, and then the red line shows the energy spectra from the model, and this is from the CFSR global model, another global model that I mentioned earlier, which some people prefer to use instead of the RO5 for this sort of application. And it seems to represent the measured data if you take a 2 hour mean of the measured data, the spectra seem to overlay. So this is used in this Metocean report to make the assumption that the extreme values of wind derived from this CFSR model are representative of a 2 hour averaging period. So that's an important step in the Metocean analysis. You usually don't have enough measured data on site to even begin to quantify extreme conditions for such regions. You know, there's maybe, in this case, there was a year or two of measured data on site, but you need to resort to a model. And in this case, a global model was used rather than any mesoscale downscaling for lots of reasons that are detailed in the report if you're interested in the DHI report. And so, but you can get estimates of the 2 hour mean wind speed during, you know, decades of extreme events to begin to make your estimate of extreme wind speed. So then you have your estimate of extreme wind speed representative of a 2 hour averaging period. But for engineering applications, you need the 10-minute mean wind speed and also the 3-second gust. And these are in the Metocean world, and I'm showing again extracts from a DHI report, but I guess there are other Metocean practitioners, some of which will be in this webinar hopefully, who will probably say they use very similar results. And if they have a Metocean background, they will usually use this iso-Fourier relationships to convert the, say in this case, 2 hour mean winds to 10-minute and 3-second gust winds for engineering design. So this is a set of relationships that's in ISO standards, but not represented yet at all, I think, in the IEC documents. So one of the things I'm trying to do here is to raise awareness of these Fourier relationships, because one thing that's important to highlight is these gust factors, these conversion factors between, you know, long averaging periods to short averaging periods, and then the gusts intrinsically depend upon estimates of turbulence intensity. And in the Metocean tradition, turbulence intensity is a parameter that you use to, you know, primarily to make this conversion. But in the wind energy industry, turbulence intensity is a parameter in its own right that has a great important bearing on wind turbine design. So a key point I'm trying to make here is these Fourier relationships that are from the ISO standards are very useful for also estimating turbulence intensity under certain conditions, not under all conditions. Another point here, Mark mentioned that enal GIP, which has been one of my primary projects that I've worked on for the last 3 years or more. One of the things we're looking at on this project is much more detailed methods to estimate gusts, extreme gusts. I'm now going to talk about some other methods briefly that are result from the work of Zali Larsen and other colleagues, primarily at Technical University of Denmark, that have developed spectral correction methods to account for the missing short period variability within these models. This graph is from one fairly highly cited paper from 2012, which compares, it's similar to the plot I showed earlier, where the initial 10-minute data has this slope in the spectra. So this is the spectral energy density versus frequency. And then if you average the observations at 1 hour, 3 hour, 4 hours, you get this reduction in high frequency energy. And then you can see that different here, this is all looking at various downscaled models of different resolutions and how they all compare to certain longer averaging periods that are longer than certainly longer than the 10-minute or the 1 hour averaging period. And one key result here is that when plotted on these axes, there's a sort of trend for the original data to have this kind of -5/3 slope. And then that's the heart of this spectral correction methods. And then another plot from another paper by some of the same authors who talk about the application of this, but to a global model. And in fact, on land, this was an application over land in South Africa, where they used a CFSR model, but they developed various ways to correct the spectra to account for the missing energy. So what I'm trying to get out here is that this is a quite different approach from the method used I've just outlined before in the Metocean report, where you find the long-term sort of 2 hour, 3 hour effective wind speed from the model, and then convert it to equivalent 10-minute or 3-second gust values. Here, these methods are looking at ways of correcting the spectra from the models to better represent the measurements. And then another slide from another study that the last wind energy conference I attended face-to-face, the last one before COVID, hopefully not the last one ever, was in late 2019. This was a nice presentation and poster that was showing how these sort of techniques are also used in the time domain to generate time series. This is some work done by EMD. I shouldn't dwell on this. Another point that this presentation made was that the errors were much smaller offshore than onshore. Okay, I'll move on from that. Okay, so I've talked a lot about turbulence intensity and wind spectra, but if you use either of those in engineering design, you're essentially assuming that the wind is effectively stationary over periods of about an hour or less, which often isn't the case. There are some very strongly non-stationary events that need to be analysed in the time domain, and I haven't got time to dwell on this. Mark mentioned this West Africa Gust project that I started working on with him probably more than 20 years ago, where we were focusing primarily on extreme winds during squall conditions offshore West Africa, and I've done lots of work on these sort of phenomena in other parts of the world. They can have a very large dominant impact on the engineering design of large floating structures. So they're a consideration for floating wind turbines as well, although the dimensions of the structure are different, so the response periods will be different. But I think that features like this are certainly a design consideration for floating wind in some form. And they need these particular features. I'll just put a graph up of one particular high impact squall event from a Gulf of Mexico study that I was involved in, that you really require rapidly sampled measurements. So taking the 10-minute mean wind speed is not good enough for capturing these features. You need the 1-minute mean, or preferably much more rapidly sampled to capture the gusts. So that's an important consideration for some of these rapidly varying events that are important in some regions, more so than others. Okay, I better move on because I'm using a lot of time. I mentioned already that the ISO and the IEC standards don't have exactly the same recommendations relating to the quantification of offshore wind. And I mentioned the Freuer relationships. It's a series of relationships that are enshrined in ISO, and how that they are potentially, they're very widely used in the Metocean world, including, in the offshore wind Metocean world, as evidenced by those DHI reports, which use these relationships to some degree. So one of the things I'm involved in now as part of this in our project, but also more broadly, is to compare how these various relationships from the different design standards and other literature compare to a large amount of measured data. So this shows on the left the 1 hour mean wind speed, in this case, profile from the IMarEST Met mast in the North Sea during the strongest storm event that impacted the region, which is the St. Jude storm in October 2013. So the solid dots show the anemometers on the Met mast, and almost indistinguishable are the ISO curve, which is, and also empirical fits to the logarithmic Z0 and power law alpha profiles. And those logarithmic and power law profiles were fit completely empirically to the data. They were just the best fit that minimized the errors. Whereas the ISO profile here can be completely determined from the wind speed at just one elevation. It's a logarithmic profile where Z0 is derived from the wind speed itself using relationships that have been empirically validated over the years. And it provides a very good representation. Another point here is the power law best fit to this curve gives an alpha of sort of a shear value, some people call it, as 0.1, just above 0.1. That's a little bit lower than the IEC value of 0.11. So that, just to raise awareness that that this ISO profile is something worth looking at. Also on the right, there's the turbulence intensity. So there's the measured data again in the black dots, the ISO profile, a different equation, which is actually there. I've put it on here. This is results that are from the eNow project, where we've had some permission to release some of these extracts in a poster that's identified there. And in this case, this prediction of the turbulence intensity profile from ISO, it matches the data very well, better than some very simple relationships you might derive from Z0, the logarithmic fit. And there's another little equation here just to highlight that the gust factor can be derived directly then from the turbulence intensity. If you can get a good estimate of turbulence intensity profile, you can then get the gust factors. But of course, for wind energy engineering, the turbulence intensity in its own right is important. I mentioned it, so I'll say a couple of words, but very briefly, because it's not the topic of this discussion. The eNow project, it's a joint industry project where we've, in collaboration with various others, have gathered a lot of the MetMast and now LiDAR data set that's available in the public domain, both in the European and the US waters, and subjecting them to a very detailed analysis, looking at how these vertical profile turbulence intensity relationships work and how the different relationships and different design standards work, looking at model validation calibration. I should move on from that, because it's not the topic of this discussion, but just for some background. Okay, extreme methodology. Now this come into nearly my last slide. So I've hopefully illustrated how, from my own Metocean perspective, where I focus quite a bit on extremes rather than normals, different methods have evolved in the wind resource and Metocean communities, and quite often different words are used to describe something that's very much the same. In discussions I've had, I think just there may be some benefit of improving the clarity of what we actually mean by an extreme event. In Metocean, it's defined just as a low probability event, so the wind speed that has a sort of 1 in 50 chance of occurrence or exceedance in any given year. However, some people would say an extreme event is one that has a particularly high gust or high turbulence intensity, so it's a sort of frontal system. And of course, in the terms of engineering design, what you really need to know is what is a high impact event on your structure. So you need to have some understanding of the structural response to quantify what is an appropriate extreme condition. And there's lots of work done in the IEC guidelines to define various design cases. One particular topic I wanted to highlight, because I've seen it, in the Metocean community, we use the terminology peaks over threshold to describe what many people would consider to be statistically the most robust method of doing extreme analysis. And that seems to go by a different name in the wind energy community, where it's called the method of independent storms. So those are effectively the same thing. And then just to illustrate how different words can be used to describe what is essentially the same thing, there's very few events in Metocean that have a larger impact on winds and Metocean in general than hurricanes, cyclones, or typhoons, whatever you choose to call them. Okay, so as I said at the start, hopefully this webinar is the beginning of a longer term discussion between these communities as part of the IMarEST, but also other activities I'm trying to push forward as a voluntary basis, and also, as part of my company. I really want to help promote engagement between these wind resource and Metocean communities, and hopefully this webinar and the discussion we'll have is a step towards that. I've mentioned the IEC and ISO standards, and increasing coordination and convergence between those may be anticipated in future, which I think will be accelerated by more of the traditional oil and gas companies moving into offshore, and particularly with the rapid growth of floating offshore wind, will maybe accelerate some of these convergences. Another topic I wanted to outline quickly is in the wind energy industry, there are clearly opportunities for more strategic data collection and sharing. As I noted, the Netherlands example is a really good example of how data are available, in advance of a project. It would be great if that sort of practice was more widely adopted. And ultimately, if we can follow all these through, we can further reduce the cost of offshore wind. And importantly, through collaborative strategic data collection, there are many other users of the ocean that would also benefit from improved observational data, which is something that we're exploring via these various special interest groups. And then just to finish, a key event that we're planning now in the operational oceanography special interest group, with strong input from the offshore renewable special interest group, is this Oceans of Knowledge event, where we're looking at climate change in the ocean. One of the key themes we're looking at is how climate change and our response to climate change is driving new increased use of the ocean space by various users, sustainable use of the ocean space. And of course, offshore wind energy is one of the key rapidly growing areas, but there are others. Another quick point I want to make is that as part of that event, we're bringing together the IMarEST with a whole range of other learned societies and professional bodies to help support and build the content of this event. And that's maybe an approach we could take for taking this discussion between the wind resource and Metocean communities forward. A lot of the Metocean community are IMarEST members, but not all of them. I expect very few wind resource. So we'd like to gather information from the people that participate in this event of what professional bodies and learned societies they are members of, because if we try to continue that discussion, it may be good to try and reach out to those other organizations to see if we can take this forward as part of a wider effort. So that's, I've spoken for 50 minutes, I think, with 19 slides, and that doesn't leave much time for discussion. So we better get on with the question and answer session. I think that's it from me. I will stop my sharing for now, but I'll go back to it if any particular questions arise. So
thanks very much, Gus. Just on Gus's point regarding other learning societies or professional bodies, if you could pop any suggestions into Slido, that would be very welcome. If we pick up on some of the questions now, the first one that came in was from Mike Osborne. Hi, Mike. Wind speed accuracy.
Yes, yeah, I could put that slide back up, but indeed, yeah, the 2 decimal places is it demonstrates the attention to the mean wind speed that is given in the wind resource community. Obviously, 2 decimal places is a high level of precision, but 1 decimal place is probably not enough to get the resolution. And getting a response from someone who's involved in the wind resource and the impacts of the wind speed on the the costing of a wind project might be important. But yeah, I think hopefully I've addressed that.
Yeah, I mean, if you look at the uncertainty that you have to actually calculate as part of the IEC guidelines, it doesn't lead you to even 1 decimal place, I don't think. The next question comes in from Johannes Gulluckson. Apologies for my pronunciation. These slides will be available after the presentation, Gus. We'll put them up on the IMarEST site.
Yes. There's a PDF version that I've already sent to IMarEST that I'm happy, and I all the material that I included from other sources, if it wasn't sort of Creative Commons, as I had specific permission to include. So hopefully that includes distributing the PDF slides. All of the links are there to the sources. So
great. Thanks.
If anybody's listening that provided material and wants to say, no, you mustn't include that, then please let me know urgently, but I've had permission, so they should be available. And very happy to engage in further discussion as well, particularly as we may be short of time now.
Moving on to the next question, Carla Ribeiro from Thistlestead, sorry. There is good reason to use 10-minute averages in wind resource assessment. Van der Hoeven spectrum indicates peak around 15 to 10 minutes, important for turbulence. Do you have any comments on that, Gus?
I would agree. I mean, 10-minute mean winds are the standard used for engineering design, and I think in wind resource assessment too. So, and yes, I guess Carla's saying there are physical reasons why that is the case. Does that, if that hasn't answered your question, Carla, then please put a new one up.
Oh, moving around.
Someone's promoted Mike's question.
Yep. Is directionality important, in particular rate of change of wind direction?
Directionality is incredibly important because the wind regime changes and all the characters of the wind change with direction. And for the rate of change of wind direction is important for some structures, for sure. In the Metocean world, we're very familiar with floating structures responding to changes, rapid changes in wind speed and direction, and ocean currents as well. That can be a big constraint, and I expect that is also the case for floating wind turbines and fixed wind turbines. I haven't looked in detail myself on the impacts of the turbines of rapid changes.
It's the turbine control, the yaw control, that's very important. There was some work undertaken by NREL which showed that as a potential failure mechanism under hurricanes.
Good. Yeah. Well, maybe not good, but thanks.
Climate change. Are climate change projections utilized to quantify future winds?
They should be, and they are being used. Thanks, Olaf, for that question. I know we've discussed this a little online. Yes, they should be, and it's an area of ongoing research, and it depends upon the region. So yeah, they should be, and they're not as widely used as perhaps they should be, but there's a lot of data there now that we can begin to look at and use to assess storm severity over coming decades. And to what extent, decades of historical data are even relevant to your site. That's a key question that needs to be addressed.
Yep. Question from Robin. Hi, Robin. Many thanks. Very interesting presentation. Would you anticipate that the findings of the ENOW GIP will result in published guidance?
Hello, Robin. Glad you could make it. Ultimately, we would hope so, but part of the objectives of the ENOW project was to provide research and development that can help improve the clarity of these relevant standards. Initially, during the initial years of the project, it's all proprietary and confidential to the people who have funded the research and development, as with any JIP, and they're not going to release that all because they paid for it individually, and there's still other companies joining potentially. So, but ultimately, over a particular time domain, there are plans emerging already, and that's part of the reason why I've become involved in the relevant IEC committees, is to provide a direct mechanism for appropriate results to be released into appropriate parts of the IEC guidelines over the next few years in some form that's not yet fully determined, but that is one of the longer term objectives.
Thanks, Gus. Another question from Johannes Gulliksen. The models for wind speed modeling, are they similar to those described in DMVGL recommended practice C205?
Yeah, this C205, that was a very good reference for wind, and generally that provides a very comprehensive summary of these various models. It actually is one of the few documents that includes a good coverage of the Fourier relationships that are included in ISO, and also it provides a bit more detail on the logarithmic and power law profiles. So, but it's not an international standard. But yeah, that document covers some of these very well.
Okay, I think we have time for one more question from Lawrence Farney of Babcock. How much do you find Metocean analysis tying into installation vessel capabilities alongside turbine design?
It's absolutely critical. But I personally haven't been involved in that, but I find many people who have, that it yeah, it's absolutely critical to all of the operations offshore as well. The turbine design and the operability are two different applications within Metocean, and you would use different streams of data and analysis methods. But
Okay, given the time, I'd just like to thank Gus for his presentation and the audience for their questions, and I will pass back to Catriona to just talk us through how we move into the next interactive world that we're living in these days.